just asking, so I think each one.
Yeah. Yeah, he is not, but I've hit the record button, so anything I say from now on at least will be recorded.
I was middleman.
One of the requirements is being able to trace some of these algorithms, like this, like I thought is what we discussed last time, maybe.
Yeah, I'm not going to require that you know the algorithm or be able to run through the individual lines of an algorithm. That's kind of beyond the scope of.
Okay.
If I were doing something like that, I would give you a project and have you actually work with the algorithm, have some back and forth. My goal with any exam like this is going to be to query your understanding, your intuitive understanding of the concepts we've covered, what the algorithm is and does at a high level, not at a line by line or function by function level. Just what is it? Why do we care about it? Why is it used? What can it do for us?
Okay.
Kinds of questions. So they will be more abstract, or where they are less abstract, I will either have an example for you to apply something to for problem solving, or ask you to generate some kind of problem where it would be used. And if you understand how it works well, then you'll be able to plug and play it into something that you are familiar with. Killing David already.
That's just Dave.
Daniel looks this next to me and I just lose it.
Right, it's Bobby.
There you go.
Then, in constraint solving, you have how do we represent constraint satisfaction problem, but below that you have variables and values, domains, constraints, assignments. Parentheses legal, completed solution in parentheses.
Yeah.
Did you just give us the answer for that? Or?
Not necessarily. So you can have a constraint graph that allows us to visualize the variables and assignments and constraints between them as vertices and edges in a graph. So that's one way to represent it, but the other way logically is through the associated variables, values, etc. But be able to break that down and analyze components of a constraint problem.
Okay, so this is for consideration.
Yeah, it would be something like if I gave you a constraint graph, I would expect you to be able to read the constraint graph, because that is on the study guide of how do we represent a constraint problem. One of the ways would be with a constraint graph, and we had the example of Australia on the slides. So if I gave you something approximately similarly sized with regards to it, how could you tackle this problem as a constraint problem? How could you represent this as a constraint problem? Then the fact that that is on the study guide, maybe you copy over some components of that to a study sheet, and then you can say, all right, the components of this are 1, 2, 3, 4, 5. Identify with the problem, what is 1, 2, 3, 4, 5? That's just kind of applying without having you memorize the components of a constraint problem, because anything that you can Google in 2 seconds isn't worth my time to throw out an exam, or your time to memorize before regurgitating on an exam, where if you didn't memorize it, then you get marked off somehow for some reason for not memorizing something that you can look up in 2 seconds. I hate that.
Can the notes sheet be printed?
Yes. Yeah, printed, I don't care about text size, write small, type small, bring a magnifying glass, I don't care.
I was gonna ask that.
Microfiche, like, we're gonna bring it in like projector with the.
Your camera can zoom in pretty darn far. I was playing around with that on vacation in Europe, was doing some really weird spying on someone in a building that was like 3 miles away. I couldn't even see them with my naked eye, with my camera zoomed into 100x, like, dang, you gotta close your window.
You do that too?
I'm just sightseeing, playing around with it. Suddenly it's, wow. You didn't realize that your window is viewable from this structure that's over here. All right, I'm gonna go look the other way.
I don't know how new your phone is, but I thought that was that. Oh, blurry, still in the room. Oh, bored.
It's fair.
Another one I have is what heuristics work well for backtracking search. Like in your slides, it seems like you only list 3, but it feels like you could find more.
Kind of a, what do those 3 share in common? What ideas lead to for backtracking search? What leads to something that works well? And even if it's just those 3, the question that I would probably ask relating to that is, what about a heuristic works well or doesn't work well with regards to backtracking search. And even that's probably a little more in depth than I'm targeting with most of my exam design. So just saying that out loud makes me feel like that seems arbitrarily specific. Kind of like you know it or you don't, or you looked at it or you didn't, and instead I prefer kinds of questions where there's many possible solutions, you can construct a solution to that, because then it also allows me to give partial credit where answers are partially correct. If it's a question that specific, it might as well be a multiple choice question, because you're either gonna know it or you won't. I don't really love questions that are quite that specific. Where I can design art. What else?
I was wondering if you could go over, I would hope it's quick, the indoor search with the vacuum cleaner.
Yeah,
Also, imagine going to the store, with a phone store and asking, I need this phone, but it needs to have 100 exit.
Yeah, that seems a little sketchy, doesn't it?
The vacuum cleaners, PowerPoint 2, slide
Yeah,
16, 17.
was in the local search.
I think he's like I don't know how to describe it.
Okay, this is the T-Mobile thing.
See, we can visualize it kind of more like the tree from this slide, maybe.
Yeah, that one, then. I think. Yeah. Full core, more vacuum cleaner one, but. The left and right side stuff, I was kind of out of it.
Probably have to do a 1.5 hour part for everybody.
Yeah, I totally understand that the way this class is set up as a 2.5 hour block of dense material is not fair. And I will argue for the scheduling of this to be different the next time I teach it, because it's not easy.
I don't think 2.5 hours like Cyber 101 would be bad, but 2.5 hours of pretty much like advanced, like algorithms theory is pretty rough.
Yeah. That's fair. So all that's going on with this is that we need to find some way to clean the rooms. And with non-deterministic actions, we don't necessarily know the future state that we're going to be in. Either it's stochastic and there's a probabilistic distribution of where you might end up, or we may be unobservable. We don't necessarily we can't see the associated state that we're in, so we have to map the belief states onto the set of actions to where we know that no matter what the state was in when we started, after we do this certain set of actions in this particular order, that the state of the world is now in a particular state. We know what the state of the world is after this particular sequence of actions. And the way we were able to do that in this case was by saying something like, if we move right at the beginning, then we know the vacuum is in the right room, regardless of whether it started in the left room or the right room. If we move right, we know, we don't know nothing about how dirty the two rooms are, but we know where the vacuum is. Now, if we suck from the right room, then we know the right room is clean. The left room might also be clean, but we don't know that for sure. So then if we move left and suck, then we know that we are done. That both rooms have been cleaned and the vacuum is in the left room. And regardless of the initial state, with that particular set of actions, we know that the goal has been reached, both rooms were clean. And that just comes from mapping this world, the belief state of that, not knowing where we are, onto an associated action set where we're in any of 8 possible worlds. After the first action, we're in 4 possible worlds. After the next action, we're in 2 possible worlds. After the next action, we're in 1 possible.
Can you go to the next slide? Why is it called an indoor search?
I noticed about
When I was looking it up, I couldn't. It said like the and is you go through an and node, you have to take into account all the possible branches that you could move to from
Right.
there. On this one, it seems like the leftmost if you go to the left. Left once, you get a goal and then some other state. And then the other state, if you go to the left from. I think it was like, it says state 5, you
Yeah.
end up at 2 loops. So I'm wondering. Why would we continue on to the right if we already hit the goals? Oh, I guess if like we don't know.
It's conditional, yeah, because you don't have, the initial state for this run is state 1, but if you don't know that for sure, or if you have some way of measuring, this gives you a conditional where if you end up in state 5, it tells you what to. If you end up in state 6, it tells you what to. And there might be times where probabilistically we end up in different places and we can measure that in this as well.
Why do we have state 7 after state 1? We can only, if we're only sucking from the left side, is that taking into account that we might not know the condition of the right room?
It comes from the rule that was stated, where was that? Yeah, right here, the second bullet point under the example. Sometimes when you use it to suck a dirty room, it gets a mind of its own and sucks an adjacent room as well.
Oh, okay.
File back.
Yeah, totally wild vacuum. Don't buy used vacuums.
Uh,
They're very unpredictable.
So we would consider that into one possible. So we put under.
Yeah, so basically we don't know if it gets a mind of its own or it doesn't, and we have to make a decision about which action do we tell the vacuum to do, despite the fact that the future of that action is a little bit uncertain.
in this situation, do we know if the vacuum gets a mind of its own and sucks both rooms?
In this one in particular,
particular,
yes, we have the ability to see what happened.
Okay.
When we talked about partial observability, which I think was after this, then we talked about belief states and trying to minimize belief states. But this in particular was just saying, we want the ability to determine and find some way of determining what action to tell the vacuum to take, given the uncertainty of that it might do a couple of different actions.
What are the circles in this that ends?
They're when we have the ability to give it they're kind of it's a chance node, where when we tell from 1, we tell it suck, and we actually don't know now if it's gonna be in state 7 or in state 5. But we make the decision to tell it to do this, knowing that we could end up here or here. If we end up here, hey, we're done. If we end up here, then we wanna move right, because that has to be the state of the world after that action and not hitting the goal. All right, does that make sense?
Thank you.
What other questions can I answer?
You go through the max again?
Yeah, minimax from adversarial learning.
I go, I mini max or my head, just I heard bin and max so many times. Like,
There's a spec to that next.
vacuum cleaner, I was a feet approved. I'm not gonna lie, vacuum cleaner, these might have done pretty well.
Yeah.
Strange.
With my vacuum cleaner.
This algorithm. Just a general overview of it, or what's anything more specific than that, or just kind of how it works in general?
Yeah, just walking through it, I can remember what the point was for each one.
Yeah, so this is a decision point for max. Anything that is a triangle pointing up, anything that's a triangle pointing down is a decision point for min. It is max's turn, and what max wants to do is to maximize the score that it gets. But before we get a score for anything, min gets a chance to counteract what max does. So max could take this action with hope that it can eventually get that 14, but because min acts here, min is gonna choose whatever is best for min. So we end up with this 2, not this 14. So from max's perspective, it wants to take the maximum of the minimums of each of these sets.
So like min gets a chance to choose 14 rather than max.
Right, once we're at D, min chooses which of these results actually come to pass.
So.
But max gets to choose which of these sets of 3 min has to choose from.
But then how does it win when it goes to the left side? then it chooses, I presume, min gets to choose first, and a B.
Right, so this is the solution to this mini max, this is what's actually going to happen. This is the end result. And the reason we know this is if max chose path A1, then min would choose the smallest of these three values. If max chose A2, then min would choose the smallest of these three values. If max chose A3, min would choose the smallest of these three values. The largest of the smallest of these three values is that one. So max chooses to go this way, assuming that min is going to act in its own best interest to maximize the end result from that perspective. And min, given that these worlds don't exist, does the best that it could do within this subworld. And that just models kind of the back and
It feels like
forth.
there's an error, because it could still go down D, still choose 2 and max within the 14, which would be the best possible result.
Why would min choose 14? Because this is the,
Min would choose 2 and then max would choose 14.
they don't get to both choose different events. Min, this is kind of an overall state. If you can imagine like a reward, like maybe I have $14, I'm going to distribute it amongst max and min. And the value that's here is the amount of money that max gets, and min gets whatever's left over. Now as max, what do you do in order to try to maximize the amount of money that you get from this system? You would know that whatever situation min is put in is going to maximize the amount of money that min gets, which is minimizing the amount of money that max gets. So if we go down this path, then min is going to say, I want to give max $3 so that I get $11. I don't want to give max $12 so that I get $2, or that both of these don't give min as much money. So min wants to go here. And if we end up down either of these paths, then max doesn't get as much money. So max doesn't want to choose A2 or A3 because it's actively hurting max once min gets a chance to act in its own best interest.
So max can see all the values that minimum picks, so he's just trying to pick some maximum.
Right.
He can.
Yep.
Okay, that was the problem.
Yeah. Yeah, it's a game that goes back and forth between max and min and max and min and max and min until the end state. And usually we don't know in any kind of game or any kind of environment, we don't know the true payouts until the very end of the process.
So in that sense, the other guys swap places until they reach the bottom.
Yeah, you can think of it kind of like a tic-tac-toe game where we don't know who's going to win the tic-tac-toe game until the end of the game. But we know that X moves, then O moves, then X moves, then O moves, then X moves, then O moves. And you can construct a really long table with outcomes based on whoever wins the game, based on every possible play of tic-tac-toe or any possible sequential activity.
See, now I'm not writing notes while listening to this, it's way easier to understand. Holy cow,
I discovered this in undergrad. I hate taking notes.
yeah,
I cannot focus on something if I'm trying to take notes on it.
that's in my class.
You have to parallelize what's being said and what's on the slide. The slides will be available. If they're not available, send me an email, yell at me. I'll make them available as soon as I know that slides aren't up. I don't want you taking notes verbatim on what's on a slide. You will have that later. Take notes on what I say, think critically about questions you can ask, clarifications you can make. Yeah, the class will go a lot smoother, I think. At least it would for me. Obviously, people are different.
I know it might be a little bit much, but can you post the slides a day or two before we go? I like rereading.
Okay, sure. Yeah, I can manage that. I can post everything that I've made so far. Honestly, it doesn't bother me that people see that in advance. Sometimes in some classes, I do throw things like problem sets, problems with answers. So if people are going over that, then you rob yourself of the ability to look at it as the problem without the associated solution to it. But I haven't done that a ton for this so far. So I'll look over slides and try to do that. But yeah, it's perfectly reasonable.
In the chapters, in the textbook.
That too. Sure.
I'm gonna be like. If it's possible.
Yeah, it's easy enough to save as a PDF.
And was there a version where you're going up instead of down, you're going from min to max?
It's when you're trying to evaluate what's going to happen, you can't think about this from Max's move because there's no value printed at this node. So you have to think about it in terms of if we end in this world, what is min going to do? If we end in this world, what is min going to do? If we end in this world, what is min going to do? All right, given what min is going to do, what is max going to do? So you do kind of build it from the bottom up in kind of depth first search order.
There wasn't a point where we did it from like Min's point of view though, instead of Max's point of view. We were good.
When we came up with, yeah, we did. We prune it from min's perspective, yes. Yeah, we did pruning from min's perspective. Because all pruning is trying to do is make sure that we don't look at unnecessary nodes. Once we know that this isn't going to be picked, then why look at other options? Because it's not a world that's going to be the optimal solution. Once we have that information, we can ignore the rest of that search. And that saves us time, saves us memory, makes us happy.
How do we know it's the optimal solution without looking at the other? I'll read through it.
Oh yeah, but like, for instance, here,
Yeah.
we know that we couldn't do it for the first one, but let's look at an actual prune,
Yeah.
like here. Once we see this too, we can prune these remaining nodes.
That makes sense.
Yeah, so here, there's no way that max would ever choose this path,
Yeah.
given that if this path is chosen, there, in the worst case, is gonna be worse than this path would be from Max's perspective.
But if two's all the way on the right side, then it's not really proving. It's just-
Right. Yeah, so we talked about variable ordering to be able to say, is there a way that we can look at the small values first? And when we talked about chess, we looked at move orderings that were likely to be considerations, like moves in chess are more frequently captures than they are tactical retreats. Or moves that are more likely to be good are captures or moving forward, positioning than retreats. So move ordering is super important, but it's very domain specific as well as to whether it makes sense. Is this just a sort? Is this, how do we prioritize which moves to look at so that we maximize the amount of pruning that we're doing? What else can I cover or go over or do more justice? I want to make sure we're solid on everything in the study guide before we go into an exam tomorrow. So we'll take as much time as we need today to do that. I'm not applying any pressure whatsoever on that. I want to make sure people feel as confident as we reasonably can.
Second half of lecture 4.
Just everything that's the second, yeah, all of constraint solving.
Yeah, we just. Quick, do we have a quick overview of constraints and organization?
Yeah.
That's where like I was struggling with those constraints. I really genuinely did not understand much before we got to constraints.
Yeah, I'll see if I can summarize that reasonably. In fact, what I will do is just, I'll make this a lot faster. If we just look at,
Constraints for my mind, you gotta put it where my note taking fell off. I'm dying.
yeah, so constraints are just extra search parameters.
Yeah.
So we have a general search to try to find constraints, say there are some combinations of variables that need to be satisfied in order to have a reasonable solution to the problem. I like to motivate this with something like scheduling all of these CS and cyber courses. So you want to make sure that courses that have the same sets of prerequisites aren't taught at the same time. You will have professors who will say things like, I have kids, I need to drop my kids off at school. I can't be teaching when I'm dropping my kids off at school. I have to pick up my kids. I can't have more than 6 hours between my first class of the day and my last class of the day. I don't want to teach back-to-back classes. I don't want to teach, I can't teach in Cheney in 1 hour and teleport to the Catalyst building and teach a class there the next hour. So all of those are constraints that minimize possible pairings of classes and times because it's not feasible for some way, shape, or form. So what might be a solution to the problem isn't actually a solution to the problem if we haven't invented teleportation for our poor professors. Or if our students are trying to take 2 different classes and they need to graduate, we can't have them at the same time and expect students to be able to clone themselves and attend both of them. So all of these become constraints on our scheduling. So how do we come up with a schedule that minimizes those conflicts or that works with as many conflicts as we can possibly build into the schedule? We use constraint solvers to do it. And this is true for any search where certain parameters of that search need to have certain values. So we talked about constraint problems as basically a search. So we're still looking over a graph. If we're using the scheduling idea, then a vertex of that graph would be all variables, which is all of the associated classes, whoever is teaching those classes, whenever that class is being offered, and the room that that class is in. And so every single variable would be assigned. So there would be times for every class, professors assigned to that, rooms assigned to that, et cetera. And as soon as we did that for all classes, that's a vertex. Edges between that would be changes that we can make to that schedule that would reassign variables. We could also consider it to be, if we allow for a partial graph, then we could make different assignments as we do that and make it turn it into a tree where nothing assigned is the root. And then when we assign a professor to a classroom at a time, that creates a branch from that. And then we just search that space for a valid, here are all the classes we need to teach, here are all the rooms that we have available, here are the different time slots that we have available, here are the list of constraints. By the time we reach a leaf somewhere down that where all of the variables are assigned to all of the values and none of the constraints are violated, then that is a possible schedule for the academic year, for the quarter, whatever it is that we're doing. So we're just setting up some kind of constraint problem in terms of we have variables that need to be filled. So each variable would be a class with its associated assignments, set of domains for each variable, something like here are the different hours that we can hold it in so that the time would have a domain of all the possible times. The room would have a domain of every possible room to hold it in. And then the set of constraints. This would be from all of the professors' communication, what they are stating they can't do. From our graduation perspective, we can't have these two classes offered at the same time. We need to offer this class at least once this year. Stuff like that. Then we said that solving this problem is NP complete. You can imagine that with the sheer size of the number of classes that need to be offered, the number of constraints that are out there, that this problem grows exponentially in scope. As you add in more professors, you add in more classes, you add in more time slots, the problem grows exponentially as you do that. So no problem solves this in general. No algorithm solves this efficiently in general, in less than exponential time. But there are certain setups of problems that we can use that we can solve in a reasonable amount of time. So the rest of this lecture was dedicated to trying to figure out when can we apply something that is faster than exponential time and is actually feasible to solve. So went into Australia, talked about doing that as a CSP, talked about 8 Queens, scheduling classes. This is a perfect example of using CSPs. We talked about the different constraint types. So if it's unary, then it only operates on a single variable. So something like a professor can't teach before 10. That's operating just on the professor's, any class that that professor could teach.
So when you say how to represent the constraint problems, you mean with the map of set theory that you have there, the has to be between x, x, y, z, such that x is.
Well, yeah, you would say something like the variables for the problem are as such, the domains for each of those variables are as such. And now we can make a graph for variables, assignments, and now here's how we can search that space to find a solution to that by navigating this graph environment that represents this constraint problem. I wouldn't have any more detail than something like that. And it doesn't even necessarily have to adhere to the exact same set format as this, as long as you can identify what the variables are. I don't care about the format of the answer, honestly. It's just a matter of, is it complete? Are you considering the appropriate concepts? So, yeah, unary on a single variable, binary operates on two variables. So for instance, one of the EE professors cannot teach in CAT, what was it, 203 because of the air conditioner for some reason. So professor can't teach before 10 o'clock in that room. Now we're starting to involve more variables that are constraints on the associated pairs of variables. Then higher order can operate on more than two variables. So I can't teach in that room back to back, but I can teach in that room for 1 hour. Now we have variables that deal with when you can and can't have that professor in that room for certain classes. Maybe it's okay for an undergrad class, but I cannot teach a grad class in that room. We get professors with some very stringent demands. Then we had global constraints, which was, I used the Sudoku all diff, but anything that affects the world as a whole, the problem as a whole. There can't be more than this many of something. Each something can't have more than this in it. Those are all diff constraints, or all global constraints, sorry, not necessarily an all diff, but they can be maximum or minimum constraints over some subset of variables. Are we good so far? Anything that I can summarize in more or better detail?
So in the Australia problem, is there only one constraint for that problem? Is that always can be next to each other? Or what?
Yeah, basically.
Okay, so that's.
Yeah.
That problem seems simple. That's so-
Yes, it's by design so that you get a sense of that, but they can blow up in complexity to something like scheduling a quarters of classes or determining which algorithms are running at which times. If you have some kind of network set up to monitor activity, then maybe you don't want these two programs running at the same time because they're going to affect how each other is reading something.
Just kind of want clarification, I'll go back through the slides again, I just was like super lost on the base level, how it worked.
Yeah. What else is important here? So we found a constraint graph that we could make for this problem. We found many solutions to it. Concept of constraint propagation, basically what can we do with pre-processing? How can we pre-process to understand? Can we eliminate particular values of particular variables before we even start? And then as we start to make assignments, we can also start to query the network of nodes and figure out, all right, by making this decision, what can I eliminate in the domains of neighboring nodes? In the domains of, it starts to propagate out. When you make these decisions, you can reduce the search space significantly so that you don't have to redo work that you've done before. So we talked about node consistency as a way of doing that. So this was the equivalent of one consistency once we talked about K consistency. So this is just making sure that everything within a single node is consistent. And there's not much you can do with that sometimes, but the example we used was assuming that we color South Australia green, and that just has to be by nature of the problem, or it's something that we've done, then we can look at the associated domains of what's around it can be made node consistent by applying the constraint and reducing the domain, because a particular selection for that node would violate the constraint that the neighbors can't have associated colors of the same level. But of course, we can't do that before we associate green, because then there's no way to know that quite. Talked about graph consistency just being every node in that graph being node consistent. We talked about arc consistency, now working with pairs and the constraints between those pairs of variables. The example we used here was something like y equals x squared. to make them arc consistent, we can start to eliminate elements of the domain such that there is a value y such that there's no possible x squared, at least that's an integer. So we can eliminate it from the set of possibilities for y because there is no such x such that x squared equals y. That would be arc consistency. You're looking at the constraints between the values of x and y because they relate to each other. There's a constraint here that utilizes two variables. So if we're looking at this and saying, are there any elements of the set y or the set x that cannot possibly have a legal combination that leads to a potential solution, even from just this zoomed in version of this single constraint? Maybe this isn't the entire problem, finding some y equals x squared, but we know in some solution to this large problem that whatever nodes we have here for y and x, whatever variables we have for y and x, a legal combination of this has to be y equals x squared. We can eliminate 8 from the domain of y because there is no such x such that x squared equals 8 as an integer.
So constraints are just classified based on the number of affected variables, and then
Yep.
node consistency is the word for one affected variable being consistent, all of those.
Yep.
And then arc consistency is for all of the two variable affected things being consistent.
Yep.
Why is it not just binary consistency?
It really should be called edge consistency because at this point you're dealing with the edge between two variables. It's just historically it's been called arc consistency, and people hate change, even if it makes sense.
I guess a couple of questions. Does arc consistency imply node consistency?
No,
Like,
not necessarily. Because we're dealing with unary constraints with the node consistency and making sure that that node is consistent with any constraint on that node. Our consistency is looking for constraints between two nodes. So if there was something in here that said y cannot be greater than 4, that has nothing to do with y must be x squared. There may be variables that adhere to this constraint that don't adhere to another constraint that operates just on y. So you'd have to query both the constraints on the individual variables as well as those that deal with constraints of two variables.
So I guess it's like this, you could have that example constraint, but then you could have a unary constraint, like x isn't 0.
Yeah.
Okay.
Yeah, and then only by looking at both of those would you be able to reduce the domain of x from that associated constraint. And then x from the constraint of what y could be, how that affects x.
And could you quickly do the difference between edge for arc and path consistency?
Yeah, so path consistency just has to do with more than two variables. So once you introduce a third variable that's in between those two variables, that can potentially be seen as two binary constraints, one that operates on this pair, one that operates on this pair, whatever's in the middle. But you can use path consistency to now start to look at more than two variables at once. So something like, we wouldn't be able to see, going back to the Australia problem, because we love our Australia problem, we wouldn't be able to see that the arc between, if we set this to be green, let's go with we only have two colors. So if we set this to be one, we set this to be another, there's no possible value for this. If we're only looking at arc consistency, then there's a legal value for this when compared to this, the other color. There's a legal value for this compared to this, the other color from this. So arc consistency wouldn't detect that there's no color for South Australia, given that this was colored green and this was colored red, and those are the only two options that we have. Because according to every arc, if this is green, then this is red, if this is red, then this is green, looks great.
That doesn't touch on Northern Territory and Western Australia about being.
Right. So path consistency would say this has to be different from this and this because these are neighbors.
Okay.
So now we're introducing a third variable that now says, if these are neighbors, and these are neighbors, they all have to be different.
Got it.
So how many variables are on the associated constraint?
was kind of thinking like, well, if you color Western Australia and South Australia. But it bothered me if Western Australia, but not Southern Australia.
Oh, they hate making sense down there. They're in the southern hemisphere. Winters are summers, summers are winters. It's just very confusing.
If you colored in Western Australia and South Australia, you came up with something, and then you would do something for Northern Territory and South Australia. I was kind of thinking it would like store the state so that if you colored Northern Territory and Western Australia with the same color, but if you're going for
Right.
art consistency, you wouldn't necessarily be storing.
So the entire purpose of our consistency is just to reduce the search space. It's to eliminate values from domains. We're not trying to solve the entire problem. And usually when we're applying our consistency, we don't solve the entire problem. But we can reduce the search space of what domains we need to look at for each variable by figuring that out. There's no way that this variable could take on this value as long as it's a neighbor to this at this point. So if we color this green, then that propagates our consistency constraints to this can't be green. Because green can't be an extra green. This can't be green because green can't be an extra green. So it eliminates green from the domains appearing here. When we apply our consistency after we've colored this node green. But for path consistency, works a little different.
Does path consistency imply our consistency then?
Not necessarily,
I was kind of thinking that, but I can't.
unless the constraint is a sub-constraint of that constraint. It would imply arc consistency if the constraints here are these three have to be colored differently. And then the sub-constraint is these two have to be colored differently. That is a sub-constraint of that same constraint that would apply it, or that would imply it.
Yeah, it's like.
Yeah, but sometimes you have a very different condition, like the neighbors can't be colored the same thing. They need a color and a number. They can't, neighboring nodes can't be colored the same, and neighboring numbers must be multiples or divisors of each other. Then you could have separate constraints associated with one arc constraint, and maybe every triple needs to add up to some value or some other constraint to the problem. In which case solving one wouldn't necessarily imply solving it. How we doing?
Reading a lot.
Yeah, there's a good bit here. So we talked about the constraint types, we talked about the example, talked about propagating. Once we've made some decisions, we can propagate via node consistency or arc consistency and eliminate values of variables that are no longer consistent with a potential solution. There is no solution if we were to make that decision that could possibly be. So we'll eliminate it from the search space and not try to assign Western Australia is green, South Australia is green. Why continue searching that space? There is no possible solution where neighbors are the same color. We've already violated that constraint. So if we choose Western Australia is green, eliminate green from the pool of South Australia, you would never assign that. There's no legal solution to this constraint problem that has that assignment. Remove it from the search space. Yeah, well, two or three.
Yeah.
Neighbors can't be the same color regardless of how many we pick. So we would have to eliminate it from contention either way. And it just makes the search problem smaller. You're not going to be looking at solutions that pigeonhole you into some way of not being able to solve the problem. You can catch that early and avoid doing all of that extra work. So each of the types of consistency. We talked about global constraints, talked about resource constraints. So these are all just different kinds of constraints. Resource constraints would be something like each professor can only teach at most 2 courses in a quarter, unless you're me or Stu most quarters. Then we talked about bounds propagation. How does a potential assignment to one variable affect the other variables? We talked about an application to Sudoku. We talked about the fact that nothing about the constraint problem formulation was unique to the domain. We can abstract from whatever problem we are trying to solve and think of it just as a constraint problem outside of that domain. And that's pretty powerful, honestly, to not have to think about the domain. The domain might create the constraints, but once you've analyzed the constraints, abstract from the domain, solve the abstract problem, reapply it to the domain, and you have a solution for the domain. We talked about, backtracking search.
This is an example.
I'm writing questions at the moment that are not targeting deep down minute details. Basically, can you tell me what a constraint problem is trying to solve, how we break it down, and be able to give me some examples of when this would be useful?
Is that a red herring statement? Opposite. Well,
I'll try not to, and there'll be some problems that dig a little bit deeper, but I'm trying to be fair as I write this, because I am observing everything that happens in class and trying to make something that is doable given the communication that I've had with people. I'm not trying to destroy you. I just want to convince you to understand the material well enough to know what you're talking about at a base level.
Earlier you said removing the domain, finding a more generalized solution to the constraint problem is a viable way to do it.
Well, the constraint problem doesn't have anything to do with the domain itself. Like nothing about the 3-color in Australia problem has anything to do with Australia.
Yeah.
So you can imagine that there is just a graph and you can completely draw how those nodes are stored or structured in that graph. It doesn't even have to do with the visual representation of that graph. You just need a graph where one node is connected to some other nodes. So we have node 1, 1, 2, 3, 4, and an island. And so this connects to all of those. And this is starting to look a little bit like Australia, but then maybe this is connected to that, and this is connected to that, and this is connected to that. And now we have the Australia problem. And all I've done is draw circles and edges, and it has nothing to do with Australia or the associated territories in Australia. But the question is now, can I color this graph using 3 colors? Or can I use 3 numbers and number each one a different number? And it ends up being exactly the same problem, but we've abstracted the domain away from it. So constraint problems are always like that, in that we don't have to consider where it comes from. Is there never an eraser? There is an eraser. So backtracking search was just what we used to know when we come up with and we find that we've created an impossible solution. There's no way to generate a solution from this point. How do we know where to go back to so that the next thing we do is intelligent? And if we brute force that, then we end up solving very similar kinds of problems, running into the exact same issues that we had the first time we did it. And so we're redoing a lot of logical work, running into the same dead ends that we were doing before. So we'd like to store information somehow, or be able to think about the problem such that we can identify where is the appropriate place to look next to continue to look for a solution to the problem. How far back in time do we look? Is it just 1 move ago? Is it 2 moves ago? Does recoloring Tasmania make any difference to whether the rest of Australia can be colored correctly? So we looked at 2 things: which variable should be assigned next, in which order should its values be tried in. We tried to determine the difference between those 2 ideas. So we used a couple of heuristics, the minimum remaining values and degree, to be able to say, These allow us to select which variable to fill next in a way that reduces the space the most that it can, and or leaves open the most possibilities that it can. There was an important distinction between that. We're picking a variable. We want to run into dead ends, fail fast. If we're not going to find a solution, then we should discover that as quickly as possible. But in terms of which value should we assign to that variable that we select as the next one to fill, we want to leave open the most room for future solutions. We don't want to constrain the problem further by picking something where we're hoping that there's only one possible solution from here if we're lucky. I don't know if that makes sense. Should come up with an example. I have a single piece of candy, and each of you is individually going to write down take or not take. And if one person and only one person writes take, then everyone gets the money. So I go to the first person and I say, now write down take or not take. No one else can watch that happen. What is the right answer? Should you take or not take? Logically.
Wait, if even one person says take,
We want exactly one person to say take.
Okay.
You don't get to communicate about this, but logically, if you can find yourselves on the same page, then you would be in a good spot. So if the first person writes take, there's only one possible solution to the rest of the problem. If every single other person writes not take or don't take. So by writing take, there's only one possible solution to the problem from here. If you write don't take, then you're open to, if one other person, it doesn't matter which other person writes take, then you've solved the problem or you get what you want. So from the first person's perspective, there is no reason to write take because you've constrained the problem to only having one solution from here. As soon as one person deviates from that solution at all, the problem is over. If you write not or don't take, then you have not constrained the problem as much. And there are more options, more ways to succeed. And everyone else, recognizing that that first person should do that, should think now that every person up until the last person is going to write don't take. So it is the last person in the order that should write take.
it's kind of counting for randomness, even though that's not part of it. What,
Yeah,
Why would it have to be wouldn't the first person doing it just be as fine if everybody else just assumed the first person did it?
think of it as a tree with the number of possible solutions from here. So the root node is the first person's choice to either take or not take. How many possible solutions are there from here? There's only one. This is going to become a linear process from here. Everyone has to not take. As soon as there's a take from here, the game ends. So there's only one possible solution. From this person's perspective, if they say don't take, then one person can say take. And that's fine, and that will have a single solution to it. But if that person says don't take, then that person can say take, and that can have a single solution to it. If that person says don't take, then so the way to maximize and put off the problem, make it someone else's problem, maximize the chance that you get the reward, is to say don't take.
But if I say, okay, wait, are we passing around the piece of paper?
No.
Okay. I was confused.
I'm turning something that could be written at the same time into a sequential task. And the fact that I've changed it into a sequential task actually gives people information, which is really strange to think about. If I just said everybody write take or don't take at the same time, you have no information, no logical connection about what anyone else is thinking or doing. But as soon as I say sequential, now you can start to break down the problem from everyone else's perspective that comes before you. So if you are that first person, this is your choice. Do I constrain the problem to have a single solution, or do I fail to constrain the problem and there are multiple solutions now for the next person? The next person can say whatever they want. If I say not take, the next person has total freedom. they cannot screw up the problem. And if they say not take, then the next person can't screw up the problem. And if they say not take, then the next person can't screw up the problem. So you propagate that all the way down the line until you have the last two people. In which case, a logical person would say pattern. I think it makes most sense for the last person to say take.
I don't think that'll work, but yeah, I get what you're
Depends on
saying.
how logical the people you're working with. But it's kind of the exact same idea with variable ordering, is that you want to, one, select the variable that is going to fail fast or fail first. So if you find a solution, you'll find it quickly. If you find that this particular variable isn't going to create a solution, you find that quickly. Because the depth of that tree is going to be shallow. The branching factor of that is going to be small.
Yeah. So wouldn't you wanna say take first then, because that does exactly
Well,
that?
that's the variable selection. The value ordering is what's saying now when you're saying take or not take. That's the value order problem. So then you want to maximize how many options the next decision has, how many options the next decision has, so that they can make an intelligent decision between more options. More options is always better.
So if we try to like take into account like the human element of that, and instead of like you can either take or not take, you either not take or you flip a coin as to whether or not you take it. If you say not take, or I guess if you say take immediately, then you have to flip, everybody else flips the coin. Possibly.
Yeah, and you're not likely to win
That's
that.
not likely, yeah. Or you could just say not take, and then, you know. If everybody just says not take except for the very last person, then. I mean, they either,
Then everybody wins.
yeah.
Which
Or-
seems to
or
be
everybody-
a decent solution to the problem. Even if there's no communication, that becomes what you all can agree on without any communication, because it's what makes the most sense.
I'd say, I think you might have to communicate this idea before.
I don't know, I think if you were to do this to us right now, I think we'd still fail somehow.
Well, I know, it depends on how logical you.
Yeah.
It doesn't matter what the first person or the second person actually does, the last person doesn't know that until everything's done. So they just assume that there's only like one possible way that they could have logically gotten down to them in the winnable state, otherwise you can assume everybody's chose it.
Yeah, no, I was just joking.
Yeah, strange.
I was just joking that if Chris Kane were to put this problem in front of us right now after talking about it, we'd still mess it up.
Oh, then, yeah, twice.
It's the human effect. But that's also why we take game theory classes, to be able to discuss why humans are so bad at this.
Humans are bad at statistics.
Yes, so bad. It's amazing. It's amazing that we let people vote.
Yeah, I still don't understand that, it's like, pick a door, and then after you pick, they ask if you want to change. I still don't understand how, like,
We can go over that. I kind of want to go over the Monty Hall problem, because I can make that make a lot more sense. Granted, we probably have a little bit more that we want to do, but why not? Monty Hall is fun.
Make that a problem on the exam, come on, please.
It has nothing to do with what we've talked about, but I think that helps people to be able to see. So Monty Hall by itself, first of all, everyone familiar with the Monty Hall problem?
Oh, I wrote, this is like probably really trivial, but in that situation, are the nodes the variables and then whether or not they take the value?
Yeah.
Or, oh,
Yeah. So Monty Hall is 3 doors, behind 2 doors is something useless. Usually we go with goat because they make the most useless sound. And behind 1 door is a car. And if you pick the door with the car behind it, great, you win a car. So initially you pick one of the 3 doors. The host reveals what is behind one of the doors, and it's guaranteed to be a goat. Then you are given the option of, do you want to switch which door you picked? Yes or no. So, for instance, doors 1, 2, and 3. You pick number 3. The host says, behind door number 2 is a goat. You are now asked, do you want to continue picking door number 3, or would you like to switch to door number 1? The question is, does it matter? And why?
It does for some reason.
It's not random, but yes, it does matter. You should switch to door 1. Door 1 has a 2/3 chance of having a car behind it, and door 3 has a 1/3 chance. Let me illustrate this with a much larger example that I think will make this clear. Do we agree that this problem is identical to there are 1 billion doors? You pick one of the 1 billion doors. Then the host is going to go down and eliminate and reveal goats in 999,999,998 doors, leaving one door and the door that you chose. Is that the same problem?
Yeah.
No.
It's exactly the same problem. The host is revealing what is behind all but one door and the door that you picked. It just happens to be the smallest possible problem that does this. So someone pull up a random number generator, Google RNG, and go ahead and type in, generate a random number between 1 and 1 billion. So,
Okay, I got 509 million.
Okay. Don't reveal it yet. So you're going to click it again. And someone else is going to pick a door between 1 and 1 billion. What is your pick? 2. All right. Now click the button. And I am now going to go, I can't pick 2 because 2 is the door that you picked. And I'm going to reveal what is behind every door except for door number 2 and door number
900 million and 9 for 67,594.
Yeah, so what is the chance now that the car is behind door number 2? Is it 50-50?
No,
Not at all.
it was 1 in a billion.
Yeah, you have a 1 in a billion chance to be lucky, but I'm going to avoid the door that has the car in it.
So did they just make it confusing by having just one removal, so it feels like?
Yes. It feels like it should be 50-50. But as soon as you blow the problem up in scope, it becomes much more intuitively apparent that there's no way that this is a coin flip. And if someone still argues that it's a coin flip, I start wanting to bet money on this with them. They seem very lucrative to me. I stop seeing them as a person and start seeing them as a retirement plan.
I guess it makes sense. That's just so funny. It's just fun.
But this is also, it shows how intuition can be used to solve problems in ways that if you can blow this problem up or see a related or similar problem, you can see how and why things work just by kind of looking at the problem from the top down or the abstract. I will have people who argue that that's not the same problem. But then you ask them to point out the differences between it, and all they can point out to is this is 3 doors and that's a billion doors. It's like, all right, well, let's bet on the 3-door problem. I still see money. I can also draw it out as a probability tree that also can help of you can either pick door 1, 2, or 3, given that you actually see there's a constraint on this problem of what door the host has to pick. So really there are only 2 paths. You pick the door with the car in it, or you pick the door with a door with a goat in it. There's a 1/3 chance of this and a 2/3 chance of this. The host now has to pick which door to reveal. If you pick something with a goat behind it, the host has no choice. They have to pick the door with the other goat in it. So their host is actually revealing no information by doing that. There's no information gained from that process. The only time they're picking at random which door to open is if you pick the car. Regardless, the one door that's left down this path, which is the path that you picked one with a goat behind it, which I'd probably leave 2 and 3, the door that's left has the car in it in this exact same path. The car, there's a goat behind the other door if you picked the one that had the car in it. It had a probability 1/3.
This sucks because it makes so much sense, but my brain just won't accept it. Like I know that it's right, but I'm just like,
So you're
I
saying
can't wrap my
that-
head around it.
What would be the next level on that?
Yeah, it's about information gain. You don't gain any information from what the host tells you. That doesn't change the problem at all. Because the host always has a door with a goat to go reveal. Which door it is makes no difference.
How would this work with like diminishing or to say if we have like 5 doors. Like I like to think of it like, I don't know if you saw MXC where they
Yeah.
raised their doors and like at first like they have all of one of the doors are passable, and then it goes down to 3, 2, and 1.
Yeah,
And
yeah, it's really interesting. I gave the billion doors example, and I think that,
I guess, like, my thing is, in the million door example, you're way less likely to have picked the right door, right?
it's still 1 over the total number of doors.
But like, if I have to pick 1 out of a billion, and I have to pick 1 out of 3,
It's much higher that you pick 1 out of 3, but it's still the right decision to switch, because you still get a value that's higher than 1/2. 2/3 is higher than 1/2, just like 999,999,999 out of a billion is higher than 1/2. It's just that 1 is measurably higher and easier to see.
you're like
Take it the
ruining.
other way. You have 2 doors. He opens the other door and shows you this code, and he says, do you want to switch? Of course, you're gonna say no, because now you have information, no, it's not in that.
Yeah, there you gain information.
Yeah,
In this problem, you gain no information from the reveal, which is a little counterintuitive.
so if we get no information from the reveal, why would we even switch to the first?
That's
Because now you have 2 options. You gained no information about what's in your case from that reveal. So what was behind the culmination of 2 doors is now mapped onto a single outcome.
I still find that hard.
oh, you didn't gain information on board, you gained information.
Right,
on
on what's on the
other.
other door, yeah.
Okay.
Yeah. So here, this says, in this case, you want to switch, for sure. In this case, you want to keep. Right? So there are 3 doors, behind one of them, car, goat, doesn't really matter which one. If you pick the door with the car in it, then you want to keep, because obviously you do that, and it doesn't matter which door the host opens. You pick the right one, that only happened 1/3 of the time. If you pick the door with a goat behind it, which happened 2/3 of the time, then I pick door 3, host reveals door 2, host reveals what's in door 3. They have no other option.
oh, so you're okay. So it's just that the whole thing is you're more likely to have picked a go.
Yeah,
So
they're more
you might
likely to
as
have
well
picked a
change
goat.
it.
So once we reduce the domain down to the car and a random door that was left, then it's more likely that the car is what you didn't pick initially, because it doesn't tell you anything about what was in your case.
If I ever
Consolidated
if I
everything you didn't pick to one option.
if I ever get put in this situation and I had the car and I chose to choose something else, you're getting a very strongly worded letter.
Excellent.
But that just seems like, still, it seems like there's still uncertainty, because if you chose door 2, it could still be a car. It's like, it could be in both states, it can either be a car, or it could be, goat, another goat.
Well, it's still 1/3 of the time, but you agree that the car is in one of these 3 doors. It doesn't matter which one it's in.
Yeah,
You still have a 1 in 3 chance of picking the door that has the car on it.
yes. But I guess I'm going into, like, see uncertainty.
I'd be pretty happy with the go.
Honestly, there's some value there, right? It'll keep you up at night.
I would eat it.
They're creepy and remarkable. You ever seen a goat, like a goat in like real life?
Oh yeah, they're creepy.
I would either eat it or train it to wear sunglasses.
And then eat it.
If I got sunglasses, I couldn't.
All right, that was a total sidetrack.
Sorry.
No, I think it's fun to go over, because it's something that logically people mess up all the time. And there's something to be gained by understanding why the problem works the way it does. And also why people might be inclined to believe it. And especially if you phrase it as a game and then let people bet on it, that people might think that I'm gonna break even on average. So why not? I'm risk loving, I'll do that. And that kind of procedure is what makes mobile games so profitable, what makes casinos so profitable.
You're ruining my dream of becoming a career gambler. So
I think I am saving you from a life on the streets. I see it differently.
It's a weak mindset. I always,
I prefer to have the lifelong and not just the weak mindset.
well, there's actually a universal truth, which is, Robert, that whatever you just said doesn't apply. He's the best gambler in the world. and he will always win.
Red.
It's always red.
Let's see.
Robert has never lost.
True. I 100% win.
We'll find a game where we can change that.
No, that's the whole point of gambling, you find your game.
The whole point of gambling is
go to the
to
casino and figure this
Yeah.
ignore every time you lose, and 100% of the time that you didn't lose, you won.
Yeah,
So
absolutely.
So Chris, you're saying if we took you to the casino, we're winning so much because you're so good at it.
No, we minimize the amount of loss because there is no such way. There is no way to win in the long term. By design.
You have to confirm your bias. You have to only pay attention to the wins.
Yes.
You've never seen a drunk Daniel double up.
You have.
You gotta explore more.
You all scare me with your gambling stories. As logical, probabilistic-minded individuals, you have way too many stories about gambling.
I think that the casino cheats and logic is actually fake.
Oh, they cheat by setting up a system where in the long term, they win more than they lose. And then the law of large numbers kicks in.
Just I want you to explain to me the logical probability that over the course of a day, I win like $200 playing blackjack. And then in 10 minutes, the dealer gets continuous blackjacks in a row, taking all of my money. How does that happen, Chris?
It's unlikely, but you would continue to play until that happened anyway.
Unlike-
So it's guaranteed to happen
That's
at
like-
some point in the long run.
Isn't that like random though? Because I could just like
It's random,
run out of
but
time to play.
Any particular sequence is guaranteed to happen over a large enough sample size.
But like,
I like how you said you continue to play until that happened because Thomas is a gambling addict.
I am. But like, for example, say I run out of time. I only have so much time to gamble.
Right.
What are the chances that I run out of time? Like when I lose all of my money compared to I run out of time when I win a ton of money.
I think you can answer that question knowing your own gambling habits and how much time you have. That is a very solvable question that you don't need a professor for.
No, I think this requires a case study. We have to go back to the casino. We have to start
I think
documenting.
Thomas is attempting to distract me from talking about things that pain him.
Yeah, thinking about gambling is keeping me together right now.
Big gambling makes it better.
Yeah. Can we just gamble? We'll just like play a game of chance.
When we get into probabilistic analysis, we'll bake it in there somehow.
Okay. Like we don't have an exam because we just gamble away.
Can your examples just all be blackjacks?
Some of them are.
I would tune in a little bit more.
I got a question that's on topic.
Yeah.
I think I just have a general misunderstanding of K consistency. Is it possible that you come up with an example? Maybe a variation of the Australian one where you can show K consistency for blackjack or not blackjack. I don't know. Blackjack.
So yeah, K consistency is just path. So path consistency is basically 3 consistency. K consistency just starts to add in more and more and more variables. And if something is strongly K consistent, then it's node consistent, arc consistent, path consistent, 4 consistent, 5 consistent, etc., all the way up to K, whatever K happens to be. So it's constraints that operate on K variables, or if it's strongly K consistent, then up to K variables.
In the previous slide, 2 variable set xi xj is path consistent with respect to the third variable xm. If a path through whatever the rest of that.
Yeah.
How would you word that for like 4 or 5 consistent?
So each one becomes a middle point between, so say you have variable, 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 variable. And you have a constraint about all 4 of these variables in some way, shape, or form. Then this variable is 4 consistent with respect to the other if for every value that you could put in, every triple that you could put in, there exists a value here that makes the set legal.
Oh, it just,
So think of this as being the entire set of what this could be, what this could be, and what this could be. And we say, if we pick this and this and this, the first element of each one of these sets, then there exists something in here that can be chosen. If there is something here, here, and here, basically there's something that can be chosen here. Or for each element of this, then there is some possible constraint within the 3 of these that lead to this having a potential solution. Otherwise, we could eliminate this and say that there is no value that is consistent with this. So let's say, I don't know. This can become the 4 coloring problem, or the something where you have more associated problems than neighbors, but you might have neighbors of neighbors and neighbors of neighbors of neighbors, where now you can't be the same color as your neighbor or your neighbor's neighbor. Or your neighbor's neighbor's neighbor. Now you have constraints that operate over the combination of 4.
Could it also be something like don't use 6 colors, or something like that?
Yeah. I like the neighbors of neighbors approach. I think that, so we can deal with art consistency and figure out if 2 things next to each other are colored the same thing based on the associated pairs of constraints. And that works for a 2-color problem, but not a 3-color problem. For this, you would say something like, these are all connected, but as such, and all have to be different colors now. So if we color this red, is there some variable here, some variable here, and some variable here that could lead to a solution? If the answer is no, then we should not consider red at all here and remove it from the domain, because there's no reason that red should ever, even if we maybe select that this is green, if this now still has red in its domain, then we're going to go through, set this to red, and continue to search in this space when we could already have shown that there is no solution here that uses red. So why set this to be red afterwards? We just eliminate it. And that way, when we make an assignment like this node is green, we won't consider this node as red anymore. It reduces the search space. But it's because there's a constraint between these 4 variables that they all have to be different colors.
So for consistency in this is sort of just like a set of the solutions, so there's only 4 variables.
It's constraints over 4 variables.
I was thinking like versus our consistency, it would just be like the solution between 2 of the nodes, right?
Yeah, we can't have neighbors be the same pair. So it's only over 2 variables because our consistency. But note that that doesn't help us with the 3-color problem. It only helps us with the 2-color problem. Similarly, you'd have to have enough colors in this in order for consistency to tell us anything useful. Which is why some constraint problems go up to 5 consistency, or 6 consistency, or 7 consistency, but that becomes a larger and larger exponential search space that is intractable to solve in general. Proving that something is strongly k-consistent is an exponential complexity problem. So we see this a lot just in optimization algorithms in general, that the general problem is intractable, and the interesting problems are intractable in the large scope, but become tractable when we consider subspaces of that. So it's important to be able to map a problem onto this subset to say, hey, we can actually generate an efficient solution to this because it maps onto this subset of this problem. How are we doing?
Does blackjack count as partially observable?
Yes, because you don't know what is the dealer's other card.
And you don't know the order of the deck, but as it deals, you get a better.
No,
lay of the deck.
yeah, you have perfect information about what's there, so you can make up, it's stochastic. In that whatever, if you say hit me and they deliver a card, you can get a sense of what the probability is that that is going to bust you or not. Based on either the information that you've seen, or if it's completely independent, if every card comes from the exact same distribution, there are an infinite number of decks in the card pool. That way history wouldn't matter, but that's stochastic versus partial information. Partial information is the card that is under there is hidden, but it's going to be consistent. Whatever it is will be the same value. Stochastic would be hit me, what comes next? With 60% probability I won't bust, with 40% probability I will bust, is making that action worthwhile.
So all I'm hearing is you would be very, very good at blackjack.
I'm good at anything probabilistic.
Well,
So why aren't you a blackjack millionaire?
because the expected value of the game is negative.
Not when
So I've
you're
never-
playing it.
No,
when
it's
someone like
still
me is-
negative, it's just really close to even. If you play blackjack optimally, you will win about 46 to 48% of the money that you, or I guess, sorry, 90, you win 44 to 46% of the time.
You said
Equal
that
amounts.
like off the sheet that they gave you, the crappy sheet with counting cards.
Both. It doesn't matter if you can't cards.
Yeah, counting brings it really close, but it still
Yeah.
doesn't bring.
Correct.
No, I don't even, but it brings it higher than,
Yeah.
Right, it maximizes your return, but it's still negative.
yeah.
Yeah,
So
that's-
I do not play negative expected value games. I just won't even touch them.
Play the shit out.
You
I'm I guess I let you decide.
show me a positive expected value game, I'm all over it.
That's cheating. Makes life too easy.
In a large
It
enough
makes
sample.
mistakes.
You can imagine though, here's a lottery. The jackpot is so large that it makes it possible to make up more than the 999,999 out of 1,000,000 times that you lose. It's just that you win $1,000,001 when you do win. It's a positive expected value game, but you're going to go through most likely more money than you have before you win once.
I don't really take it.
If we agree to play that game, it's just that you're gonna owe me $1,000,001 and the one chance out of 1,000,000 that I win. Other
So
than that, I'll just keep handing you ones.
would you or would you not play a game of tic-tac-toe against a chicken with high stakes?
Oh yeah, I can't lose a tic-tac-toe.
I believe you.
Casino then.
It is impossible to lose at tic-tac-toe if you know what you're doing. It is the most boring game out there.
I'll show you like, let's do double layer tic-tac.
Yeah, yeah. As soon as you make it more interesting, there are ways to make it more interesting. I honestly just think we all needed a day to not focus on
The-
crazy amounts of.
So there has been I've come back from the pits of despair just slightly,
Yes,
but as soon as I'm like, oh, I actually have to like study again, that we're back into the pits of despair. They're gonna be all good. We talked about gambling a little bit. That put a little bit of a smile on my face. I want to watch you play tic-tac-toe because that just sounds interesting.
no, it just sounds more interesting than studying for an exam, let's be real. As soon as you have real options, that doesn't seem too terribly attractive anymore.
I guess you're right.
Tic-tac-toe with a timer.
No, I just like,
Like a 10 set.
I'd lose.
So me asking a gambling question, because you're so good at this, is baccarat truly 50% though?
I actually do not know off the top of my head.
I've always wondered about that, it's like the whole people play it.
Yeah, I do not, I'm not terribly familiar with it, haven't done the research. Anything else we can cover with respect to the exam or with respect to anything before we dive into new
Sorry.
content for 30 minutes? Yeah,
One last thing with the last is you have a question that says as pattern consistency, K consistency. I've already answered that.
yeah,
Then you have what is the biggest issue using them? And there seems to be on the K consistency slide at the very bottom and very minimal. No, not that
Yeah.
one. Wait, maybe what's that one?
it is. And be completely
Constraint
general.
constraint satisfaction. Is that applicable to both path and K, or is that just a K?
Well, it's in general to both. If you want to say that something is strongly K consistent, then it's going to take you an exponential amount of time to be able to answer that question. So you can go through an individual like node consistency, arc consistency, path consistency, and that's fine. But as soon as you want to go through node and arc and path and 4 and 5 and 6 and 7, then it becomes exponential in nature. So usually what we do is we do a search step. So we're going to make a particular assignment to a variable, give it a value, and then we're going to run node consistency or arc consistency or path consistency, something that is going to eliminate some of the domains of the search given the assignment that we just made. That's going to eliminate significant swaths of the search space and make sure the next thing that we assign is going to not immediately lead us or doom us to failure. That in a way that arc consistency could have told us was going to happen, or path consistency would have told us was going to happen in advance. It's just about trading off the pre-processing that you're doing before you make an assignment with how much time you could have spent searching that space in the time that it took you to run arc consistency or path consistency. There's always that trade-off. Anything else we can cover before we dive into at least a little bit of content?
You'll be in your office long, right?
Yeah, I'll be in my office I do have to finish writing and printing the exam for this class. I've done some of it, but not all. Right?
Go over one of the questions on the exam.
But before I dive into that, I think I should give people at least a little bit of time to get up and stretch. We haven't officially had that. I noticed that some people are doing that but some of you have been sitting for quite a while, could use a few minutes. So let's take a few minutes and then we'll come back and try to at least finish off this slide deck.
Can I use a marker of yours?
Yeah.
Are you gonna
Here,
play
which color?
tic-tac-toe?
Yeah, I want to tic-tac-toe.
Wait, are you playing tic-tac-toe? I wanna watch him win.
Yeah.
What is he doing?
I'm familiar with this. Basically, the sub game, if you win the sub game, then you mark the cell in the second game, in the outer game.
Can you do this?
And yeah, because you lose the imbalance now of how many X's and O's are guaranteed to be there. You love gambling on this. How much money are you putting on this?
I don't know how turn one starts.
He knows what he's doing.
Or not turn one start, turn two, so if I play